Hello everyone, welcome to another section of the measure theoretic probability. So today on lecture 10, we will be talking about Borel, Cantelli, Lemmas. So we focus our attention on the first Borel, Cantelli, Lemma, and in lecture 11, we talk about the second Borel, Cantelli, Lemma. But before today's lecture on BC, we talk a bit more about Lemma of an event and Lemma of an event to help us understand Borel, Cantelli, Lemma. Okay, so these are some properties of the lim sup and lim inf of an event. So if you have the lim sup of the indicator function of an, then it's equal to the indicator function of the lim sup of what? Of an. And if you have the lim inf of the indicator function of an, it's equal to the indicator function of the lim inf of an. And interestingly, if you have the lim sup of an, then if you take the complement, it's equal to the lim inf of an complement. Always note that this is true, that if you have the lim sup, the lim inf of an is a subset of the lim sup of an. The lim inf of an is a subset of the lim sup of an. So if lim sup of an is equal to lim inf of an, we say that the limit exists, and we write the limit as, so the limit of an will be equal to the lim sup of an, which is equal to the lim inf of an. So since we know that the lim inf is always a subset of an, then it's clearly the limit exists. If and only if we could prove that the lim sup of an is a subset of the lim inf of what? An. So the first case is true. This is true, so it suffices to prove that the lim sup of an is a subset of the lim inf of an. Then we prove that the limit of the event exists. So these are examples on the unit interval where we construct some sequence of events of an in it. So if we pick the whole space to be 0, 1, then we construct some sequence of events. So we could have 0, 1 over n, 1 minus 1 over n, and 1. Okay, so the third example we will be explaining. Okay, so what do we mean by the third example? Okay, so we toss a coin infinitely many times. If an is the event that the nth toss is his, then what is the event? What is the event lim sup of an? So the lim sup of an is the event that we see infinitely many hairs. Remember that we talk about the worst explanation of these lim sup and lim inf. So we just apply these into what the event of lim sup will be. All right. So let's talk about some important theorem. Okay. Okay, so for any sequence an, where n belongs to the set of natural numbers, then the probability of the lim sup of an is less or equal to lim inf of probability of an, less or equal to the lim sup of the probability of an, and less or equal to the probability of what? The lim sup of an. And if an approaches a, imply the probability of an also approaches probability of a. So we prove this theorem, but 2 follows directly from 1, so it is enough to prove 1. And by this, we know that of what? The proof for 2. So let's prove 1. Note lim inf and lim sup, their definition. So if you have lim sup of an event, it is equal to, that is the intersection of the countable union, the countable intersection, countable union of what? Some AKs. The lim inf is also what? The countable union and countable what? Intersections of some AKs. Alright, so we divide this proof into 2. So we prove this part and we prove this part and we join them together. So we consider some sequence Bn and define it as what? The intersections of these what? AKs, where k runs from what? N to infinity. So here we pick this part. Okay, so we pick this part, and since we union this part infinitely, we union this part countably, then you realize that it is actually approaching the lim inf from what? From below. So we apply the continuity from below to prove that. So then we have the sequence. The sequence Bn is a subset of what? The sequence of what? An, and hence by continuity from below, we have the probability of An is what? Is greater or equal to the probability of what? of Bn and we take the lem m for through them, realize that Bn actually what approaches the lem f of An from below, so we replace it by that. We are done with what the proof for this. Similarly, we take the set of Cn and define it as what the countable union from k from n to infinity, and by definition, so this aspect you are going to the lim sup side, and the lim sup definition is that you take the countable intersection and countable union, and since you are picking this aspect, if you intersect this, it actually decreases it. So Cn actually decreases to what the lim sup of An from what from above. So then realize that the Cn is what is a superset of what of this An, because if you intersect the countable union, it shrinks it. So Cn is a superset of what of this An. Okay, so if you apply the probability to it, so probability of An will be less or equal to the probability of what Cn, and you take the lim sup through. If you take the lim sup through, you're going to have lim sup of the probability of An less or equal to the lim sup of the probability of what Cn. Note that Cn actually decreases to the lim sup of An. Then we have the probability of the lim sup of An. All right, so lim sup of probability of An is less or equal to the probability of lim sup of what An. All right, so this ends the proof for the theorem. Okay, so now let's talk about the first Borel Cantelli lemma. What does it say? All right, it's an interesting result. It says that if the sum from 1 to infinity of some sequence of the probability of some sequence is finite for some sequence of events An, then the probability of the lim sup of An is equal to what? 0. So in words, in this case, the set of points that happen infinitely often has probability 0. So if you have some sequence of events and if you sum the probabilities and the probabilities are finite, then the probability of the lim sup of that event is what? Is 0 by the first Borel Cantelli lemma. So we are going to consider some example and prove the lemma as well. Okay, so let's consider some example. Consider tossing the sequence of coins. So let An be the event that the nth toss results in heads. Okay, let us assume that the probability of An is equal to 1 over n squared. What conclusion can we make when we apply the first Borel Cantelli? So we should be able to prove that the probability of An is what? Is the sum of the probabilities of An is finite, and if that happens, we are done. Then the probability of the lim sup of An is equal to what? 0. So since we have some probability of An equal to 1 over n, then it implies that if we sum over these probabilities, we should get a finite number. So as the probability of An decreases, such that the sum from n from 1 to infinity of the probabilities of An is finite, remember that this is equal to 1 over what? N squared, so we place it here. And when you sum over 1 over n squared is equal to pi squared over 6, which is what? A finite number. Then we obtain that the probability of seeing an infinite number of hairs is what? 0. That is the probability of the lim sup of An is what? 0. We are done. Okay, so the proof of what? The first Borel Cantelli lemma. The proof of the first Borel Cantelli lemma. We first note that when you sum from k from 1 to infinity is finite, implies that if you take the limit as n goes to infinity from k running from n to infinity, we get the probability of, if you sum, probability of ak is equal to what? Is 0. Now, since for any k we have that the lim sup of An is a subset of the countable union of what? Of k from n to infinity of ak. Remember that the lim sup is always a subset of the countable union because we take intersection of the countable what? Union. So this, we pick the countable union aspect, and if we intersect the countable union, it should be a subset of what? The countable what? Union. So this is always true. So that the probability of the lim sup of An is less or equal to what? The probability of the union from k from 1 to infinity of ak, and by countable subadditivity, we have it that it's less or equal to what? The sum of k from n to infinity, the probabilities of what? Of these ak's. Note that we've already proven that the limit as n goes to infinity of the sum from k from n to infinity, the probability of ak is equal to 0. So this implies that this set this sum also what goes to 0 as n goes to what? Infinity. As n goes to infinity. As n goes to infinity. Since this goes to 0, we know that the probability of any event is greater or equal to 0. So since you have the probability of the event also less or equal to 0, then it implies that the probability of the lim sup of an is 0. Is 0. This ends the proof. This ends the proof. And see you on the second Borel Cantelli lemma and some examples. Have a nice day. Bye bye.